and this is my Graphics and Computational Programming Unit assignment presentation. We'll begin by discussing my theories, the design, I'll show a quick demo, and then an analysis and evaluation of my work. So in this theory section, we'll go over the closest point intersection equation and then move on to multi-thread distribution. So this is the closest point intersection equation, which I use to help render my spheres onto the screen. On the next slide, you'll have a visual graph to help me explain how this equation works. Simply, we get the dot product of the vector from the raised origin to the sphere center and the raised direction. We then subtract the distance from the closest point of the ray to the intersection point, and then multiply all this by the raised direction to convert to a vector. We then add in the displacement from the ray's origin. This equation will be what my program uses to help render the spheres to the screen. Next, let's talk about multithreading distribution. A thread is a sequence of operations performed by the computer, and a program can create multiple threads to perform them at once, which reduces the time for a program to run, since the workload is shared between different processes. If multiple processes require the same resource, a mutex can be used, which locks processes until the resources become free again. This can speed up processing time and can optimize operations that take time. However, it's easy to mess up due to complexity in larger thread applications and can cause synchronization issues that are hard to debug. This is a simple diagram explaining how multi-threading distribution can work. When a program initializes its functions, it splits the workload into two threads instead of one, with an optional mutex in case the two threads require resources that need to be shared. After both processes are completed, they move on to the post-multi-threading operations before outputting to the screen. Multi-threading distribution has many use cases in the industry. Increasing the overall speed of a program by dividing workload across multiple threads means that it can handle large amounts of data in a fraction of a time that a single process would. In this section, we'll talk about recursive ray tracing, ray-level parallelism, and column-based rendering as part of my design for the program. Recursive ray tracing is when you create more rays after the initial hit point to achieve a more realistic lighting effect. With recursive ray tracing, it allows my program to have more features such as reflection and shadows. However, it could be improved to include refraction and transparency material effects. Ray-level parallelism is a feature of my program that allows me to handle multiple rays at once using multi-threading. Individual rays can be rendered to the screen as they are self-contained and do not need information from other rays to make their own calculation. Column-based rendering is another feature in my program that lets me simultaneously render sections of the screen separate from each other. I split the screen into columns and divide the workload into individual threads to process their own tasks. Here is a demo of my program. As you can see, a variety of lighting options are available to be used, such as ambient, specular, and diffuse techniques. As well as a number of material properties, I have included metallic and gemstone spheres to showcase the range of realism my program is capable of achieving. Aside from this, a perspective camera is also utilized, as can be seen from shapes being in front of or behind others, as well as shapes being able to be rendered by colliding with others. In this section, I'll talk about the analysis of my performance stats and visual quality for my program. For my performance stats, I decided to calculate the time it takes to render the scene with different threads. I used functions such as SDLGetTicks to keep track of the time it took for the program to render onto the screen and recorded the time to be plotted onto the graph. As you can see, only one thread makes the program take a considerably long time compared to larger numbers. However, after adding 20 threads to the program, the value of each thread diminishes notably, which is likely to be from multiple threads competing for memory and the computer being unable to handle so many threads at once. I found it interesting that the thread counts of the 100, 140, and 180 marks provided anomalous times. However, I cannot find an explanation as to why they do not match the rest of the trend. For my qualitative analysis, I took two images using differing amounts of recursive rays. Adding more rays increases the quality of the overall image, but if not programmed correctly, can lead to infinite ray traces and a slower program. As you can see from these diagrams, the image on the left has less recursive rays after the initial hit, rendering a scene comparative to an unlit scene in rendering software. Materials are too similar to tell which are metallic and which are gemstones, and the darker materials look too similar to shadows in the scene. Comparing this to the image on the right, the darker materials are more clearly identifiable to the shadows, and the gemstones are much more unique in terms of surface properties compared to the metallic materials. Finally, I've learned through my finding that more threads does not necessarily mean more efficiency, since they can eat up memory without any worthwhile returns. What's more, Ray reflections are also useful, but only up to a point, since a large number of reflections would not be visible in my program. Ultimately, if a fast render was required, I would recommend 5 to 10 threads and 3 ray bounces. However, if time is not an issue, it may be worth increasing the ray bounces to 5 or more to give a more realistic and high quality result. If I was to continue this endeavor in the future, I would add in softer shadows and some more refraction techniques to help enhance the program. This marks the end of my presentation, and I thank you for your attention.